Humanity is ready to return to the moon for the first time in more than 50 years. The challenges, danger, and sheer determination to mitigate and overcome these challenges is reminiscent of the heady Apollo days. But firstly, we need to see the immense distances that they will cover. And perhaps to understand the magnitude of the Artemis II mission, we have to look back to its closest historical ancestor, Apollo 8. While both missions represent a first for the respective generations, the technical paths that they take are significantly different due to the hardware and safety protocols of the eras. Let's do an Apollo 8 versus Artemis II comparison. While both missions aim to carry a crew to the vicinity of the moon, the trajectories and mission objectives reflect different engineering philosophies. So the clearest difference is that Apollo 8 dropped into a low lunar orbit, whereas Artemis II does a free return trajectory only. Well, the final destination is the lunar South Pole for three reasons: water, sunlight, and communication. Water ice is thought to be in permanently shadowed regions, though how much is a little bit of a debate currently. But think about what you can do with water. You need water for everything, for life, for cooling, for rocket fuel. Everything. It really is the game changer. There is, on the ridges, perhaps near the Shackleton crater and other places, near continuous sunlight, and this gives reliable power. It doesn't have the brutal 14-day heat and 14-day night that you'd get closer to the polar regions. Also, on one or two very high peaks, you have a near direct line of sight for near constant communication. Certainly initially that would give both high speed and very reliable communication. One of the most distinct features of the Artemis II mission is the 24-hour loiter in a highly elliptical orbit. But others raised some sharp points. Why no lunar orbit on Artemis II? Is it just fuel shortage from boil-off? Why is Orion less capable than the Apollo command and service module? SOS block seems weaker than Saturn V. These are all great questions, and let's just hit one by one. Let's take them head on with facts from NASA docs, trajectory analysis, and mission planning. Now, this isn't defending or criticizing. It's explaining the engineering trade-offs. First, the big one was Artemis II skips lunar orbit because of fuel limits, not just safety. And the answer is partially true. But safety is the root cause. Unlike Apollo 8, which went directly after Apollo 7's thorough Earth orbit command and service module checkout, Artemis II has no prior deep space crew test flight. So NASA built in 24 hours in a high Earth orbit for full checkout of Orion's life support, radiation shielding, etc., and even proximity ops with the spent ICPS as a docking proxy. Now, this loiter means cryogenic liquid hydrogen and liquid oxygen in the ICPS boils off significantly. Hydrogen is especially prone over hours in space without active cooling. Result? The ICPS can't do the full TI load burn like Artemis I or Saturn IV's S-IVB. Instead, it's a multi-trans-lunar injection. ICPS does most of the orbit raising and initial push, providing the bulk of delta V to get to this high apogee orbit. Then, Orion's service module finishes the TLI with. This leaves the ESM with limited reserves, no real margin for dropping into a low lunar orbit and then escaping again. Safety checkouts override max performance. Better to test close to home than risk deep space with unproven systems. Let's go back to the next question. Now, comparing hardware, Saturn V's S-IVB upper stage was massive and powerful, We can see it here. It could send 45 tons to TLI after the parking orbits with a high-thrust J2 engine and generous margins. On the other hand, SLS's Block 1 ICPS, which is really a modified Delta IV upper stage with a single RL-10 engine, delivers 27 to perhaps 30 tons to TLI under these conditions, less capable due to its size and design priorities. Apollo's service module had somewhere between 2,500 and 2,800 meters per second of delta V. This is significant amount of redundancy. What about the Orion European service module? Perhaps in the region of 1,200 to 1,500 meters per second. So this is more optimized for flybys, NRHO docking and later missions, and reliance on future landers. But how does Orion efficiently escape Earth's gravity to reach that free return trajectory? It relies on a classical orbital mechanics hack known as the Ebert effect, burning at maximum speed for way more energy gain per fuel drop. Let's break it down step by step and see why exactly how NASA uses it for this mission. So simply put, the Ebert effect is the effect where the greater the velocity of a spacecraft relative to the planet, the greater the increase in kinetic energy, hence total energy for a given amount of fuel, for a given amount of delta V. Now let's take an elliptical parking orbit. It's stable and it has two very important points. A point which is furthest away from the Earth, and we call that the apogee, and the closest is the perigee. Now, in this stable orbit, the total kinetic energy and gravitational potential energy are constant. You add them up, and it's constant. Now, gravitational potential energy is based on the distance. The further you are from the center of the planet, the greater your gravitational potential energy. We're going to be a bit simple here. It's a little bit more complex than that. In kinetic energy, the faster that you are moving, the greater your kinetic energy. So, at apogee, you're really far away. That means a high gravitational potential energy, hence a low kinetic. When you're at perigee, when you're closest, you have a high kinetic energy but a low gravitational potential energy. So let's see if we can illustrate this. Now, for an impulse burn, and what we mean by an impulse burn is it's the force of the burn is the only significant factor increasing or decreasing the kinetic energy. So for the same amount of fuel, you'll have the same change in momentum, you'll have the same delta V, no matter what your initial velocity is. And that's quite important. Now let's take a very simple example. We've got something at perigee, which is moving at 20 meters per second. Now when it moves out to its apogee, it's at 10 meters per second. And we're going to give an impulse burn at both places of 10 meters per second. So at perigee, it increases from 20 to 30 meters per second, and at apogee from 10 to 20. And this rocket is very, very small. It's only 2 kilograms, and we'll explain why. Now, the kinetic energy is 1/2 mass times velocity. I've set the mass at 2 because 1/2 times 2 is 1, so therefore it's very easy to calculate the velocity. The kinetic energy is just the velocity squared. Now, let's look at change in kinetic energy. So at perigee, goes from 20 to 30, so that ends up being 30 squared minus 20 squared, which is 500 joules. Look at apogee. For the same delta V, we end up with only 300 joules. So at perigee, the impulse burn of the same delta V, the same amount of fuel, provides a far greater increase in kinetic energy, hence total energy. And that's the point. And it's that increase in total energy which converts into an increased apogee.
The Ebert effect isn't magic. It's smart physics NASA exploits for Artemis II. With the launch possibly days away, this could be the most efficient escape burn in decades. Which orbital trick surprises you most? Comment below. If you like this, check my Apollo 8 versus Artemis II trajectory comparison for the full path. Hit like or subscribe for live updates post-launch.
Have you ever wondered why a spacecraft returning from the moon directly enters the Earth's atmosphere with huge amounts of thermal heating to be taken care of by the heat shield? Why doesn't it enter an Earth orbit, dock with the ISS or other space station, and then the astronauts just return normally? Returning from the moon, the spacecraft needs to slow down by about 3,200 meters per second to enter an Earth orbit which aligns with one of the space stations. This creates a huge fuel penalty. And not just for the stage that needs to slow down. This also creates a fuel penalty for the upper stage that needs to insert lunar insertion to the moon. And it creates another fuel penalty for the huge first stage with boosters that needs to lift the upper stage and the stage which we call the command and service module for the rest of the burns. So let's have a look graphically how this would work out for an idealized mission. To launch from the surface of the Earth to LEO takes about 9,500 meters per second of delta V, including things such as gravity losses and drag. Then from LEO, a TLI of about 3,200 meters per second is required. Then when it gets to the moon, there's a further about 600 to get into a near rectilinear halo orbit, and about another 600 to get back out. That's the current option. The second option requires an additional 3,200 or so to enter a Earth orbit to be able to dock with the space station. Now let's break this down, how this extra fuel impacts the size of each stage. So using here the rocket equation, what I've done is I've broken this up into the three stages, methyl ox for the first two and hypergolic for the upper stage, with a 15-ton command module that includes life support, heat shield, and obviously space for the crew. Now let's have a look at it as a chart. These here show each stage, its fuel, and the mass that the engine has to do. So if you look at the current and you look at the Earth insertion, there is a significant difference. Now I've based these with a 10% tankage for the upper stage and the command and service module, and a 15% tankage for the first stage. Now let's have a look at it in terms of stage by stage. So on the left we have the aerobraking, and on the right we have the Earth insertion. Have a look at the difference in terms of fuel and the total size. It becomes very quickly apparent that the total mass would be 2.8 or almost 2.9 times greater for that extra 23% of delta V required. Now here's the real kicker. You'd still have to have a heat shield. Why? Because if you're coming back to the Earth and there was a propellant leak, or for some reason your engines didn't fire, you would still need a backup heat shield. Otherwise it would be catastrophic for crew and spacecraft. Now this is my idealized rocket. The rocket would have actually a very similar mass to orbit efficiency as a Saturn V and the SOS Block 1B. But if you want to change the numbers around, or you feel something should change, drop a note and let us know. Artemis I was the first crewed spacecraft to use a skip entry. Now, to understand what that is, please see this video here of what is a skip entry, and it compares it with the Apollo era lifting entry and a ballistic entry. Now, the skip entry allows a spacecraft to both extend the time but also the distance from when it enters the atmosphere to it eventually lands. A recent interview by NASA came out that during the skip entry phase, it had excessive liberation of gases in the ablative heat shield. this was greater than the permeability or greater than the ability for the gas to actually diffuse out. So you ended up having some issues with pressure buildup, cracking, propagation of cracks, and therefore the ablative heat shield, rather than just gradually being liberated, you actually had chunks that were liberated. So it appears now that they're going to work on a shortened entry. That means a maximum of 1,775 nautical miles from the point of entry into the atmosphere to landing, and a minimum of 1,300. Now it says below 1,300 is a ballistic entry. Again, see the video. So the question is it going to be a proper skip entry coming back out of the atmosphere? It seems like it might be by there, or will it be guided, or what we might describe as a lifting entry, where there is an element of lift, but it stays within the atmosphere? Be very interesting. That stays within the outer atmosphere. Be interesting to see. Certainly a lot of work went into deciding what was wrong, looking at what was wrong, doing actual testing on the vehicles, and understanding. This is obviously credit to the NASA engineers. Let's see what happens with SLS. Certainly we hope that it does launch, and the Orion capsule, being the only crew-rated capsule to beyond Earth orbit, is used.